take a look at a problem to see how all this works out. We're going to look at a single rotating object, here an old LP or long play record, which many of you may have never actually seen in person, rotates at 33 1/3 revolutions per minute. We're asked to find the angular velocity in radians per second. So the first thing we want to recognize is this 33 1/3 revolutions per minute. This is some sort of a velocity, and it's discussing revolutions per minute. So revolutions aren't a physical distance, they're a portion of a circle. A full revolution is one entire trip around the circle. So what they're giving us here, as with 33 1/3 revolutions per minute, is an angular velocity. It's just in revolutions per minute instead of radians per second. So we just need to convert the units. This is just like one of those chemistry problems you guys have, or physics problems. So we're going to take our angular velocity, which is 33 1/3 revolutions per minute, and we're going to multiply it by a couple of conversion factors. We need to get rid of the revolutions. So 2 pi radians is the same as 1 revolution. And there's 60 seconds in every minute. And when we multiply these out, you'll see how the revolutions cancel out and the minutes cancel out, and we end up with radians per second. So multiplying through, we end up with 1 1/9 pi, which is approximately 3.49 radians per second. Okay, the second thing we're going to be asked to do is find the angular velocity and linear velocities of the record per second at the point at which the needle is located when it is just starting to play, 14.5 centimeters from the center. So right here is where we're trying to find the angular and linear velocities of the record. Well, the angular velocity, we should recognize this is where Calvin's mind was blown. Both at the center and at the edge, we're still covering a full circle in the same amount of time, no matter how far away we are from the origin. So our angular velocity is the same no matter how far away we are. So our angular velocity is still that 1 1/9 pi radians per second. The linear velocity, here we use the formula up here. Linear velocity is the radius times the angular velocity. So first, all points on the same rotating object have the same angular velocity. So we still have that 1 1/9 pi radians per second. But we're going to use that to find our linear velocity. Linear velocity is the radius times the angular velocity. So our radius was 14.5 centimeters. And we're going to multiply that times the 1 1/9 radians per second. Now that 14.5 centimeters per radius. One measurement of 14.5 centimeters is the equivalent of 1 radius. So our radians cancel out and we end up with centimeters per second. And when we do the multiplication, we should end up with 50.6145 approximately. Finally, they're going to ask us to find the angular velocity and linear velocities of the record per second at the center of the turntable. All right, they keep asking us for the angular velocity at different points on the record, but as we've stated, the angular velocity is the same no matter how far away we are from the center. So even if we're at the center, we're going to have the same angular velocity. So our angular velocity will once again be 1 1/9 pi radians per second. The linear velocity at the center of the table, since our linear velocity is the radius or distance to the point from the center times the angular velocity, if we're at the center, then the distance here in the formula is just 0. So our linear velocity is 0 centimeters per second, because we aren't traveling any physical distance when we're at the center. We're just spinning around in place.